Now, how do you compute the column space? Or what does it even mean to say compute a space? So let's take an example here. So I have a matrix here. It's a 3 by 3 matrix. So in this case, rank is actually 3. And if you run the Gauss-Jordan elimination, you will get, let's do the Gaussian elimination first before Gauss-Jordan elimination. So how do you do the Gaussian elimination? You will take the first row, scale it by 5, subtract from the second row so that this guy goes away. That becomes 0. And there will be some number here. And I'll take the first again, scale it by 13 and subtract from the last row, third row. So this becomes 0. And again, some number here. Now, but these two guys are zeros. The ones with the dashes next to them are zeros. Now what would I do? I'll take the second row here. I will scale it by the appropriate number and subtract it from the third row, the modified third row, so that this becomes 0. So I can make that also 0. So I'll have a different number here. Now what I will do is I'll take the first row, scale it in such a way that my pivot here becomes 1. It's already 1, so scaling is by 1. But I have some number here in the pivot in the second row. I'll scale it so that that becomes 1. It's always possible. And scale the third one so that that becomes 1 also. So I got 1, 1, 1 and 0 below. So I have this guy to be 1, where 19 used to be. That is 1 now because I scaled it. Now I'll take that and I'll scale it by the appropriate factor so that whatever number I have here is a scaling factor. Then I'll subtract it from the second row so that that becomes 0. So this has become 0. In the second row I have 0, 0, 1, 0. I'll take the second row, scale it by 2 and subtract from the first row. So I'll get 0 here. Then I'll take the third row, scale it by 3 because I have 1 there at this point. Scale it by 3, subtract from here. And then I'll get 0 there. So I'll get 0 there. What I'm saying is that each row will have a pivot because it's a full rank matrix. And I can use the pivot to back substitute and get zeros all above. And I can scale the pivot rows such that the pivots become 1. So I can always get zeros above and can make the pivots 1 by scaling. That's why a full rank matrix, full rank square matrix will always row reduce to an identity matrix. So it is full rank. What's the column space of A? So remember, I need 3 entities. I need to know that it is a subspace of some containing space. In this case, it's a subspace of R3, but it's a special subspace. It contains all of R3. So column space is all of R3. And my recipe was that I would take the pivot columns of A as the basis for that column space. But it is all of R3. I have a better basis for all of R3. That would be the identity matrix. So I might as well say that the identity matrix is the basis for my column space. So that is what it is. Now let's take a slightly different example. It's basically similar to A, except that I killed the last column. So I have only the first 2 columns. Now let's do the row reduction here. First of all, what's the rank of the matrix? The rank is 2 because there are 2 columns and they are linearly independent. What's the reduced row echelon form, RREF, of this matrix? It becomes an identity matrix near the top and 0 columns in the bottom. Again, because each column in this case has a pivot, and I can use the pivot to get rid of the element below and above the pivot. So I'll get rid of, I mean make it 0. So I get 0 everywhere other than in the pivot positions. And then I can scale the pivots to make them 1. So that is always possible. It's a full column rank matrix because I have 2 columns and all columns are linearly independent. What's the column space of this guy? The column space, remember each column is a member of R3. So the column space is a span of those vectors. So it's going to be a subspace of R3. In this case, it's a 2-dimensional subspace because there are only 2 vectors. So these 2 vectors will form some plane in R3. That is a subspace. That is the column space of this matrix. So the dimension of the column space is 2. Now, if you look at these 2 vectors, they are in some random direction in R3 and the plane is in some orientation with respect to that. I cannot take the columns of this matrix and say that that is the basis because if you think about it, the first column is basically the x-axis. It points along the x-axis. The second one is along the y-axis because the second element is 1. But my column space is not the xy plane, it's some other plane oriented with respect to the axis specified by these 2 vectors, which is why you have to go back to the original matrix to get a basis for the column space. Now let's take one more example where I have a wide matrix. I have 2 rows and they are linearly independent. And therefore the rank is actually 2, which you can see if you do RREF, if you do Gauss-Jordan elimination, you will get 2 pivots. So you can see that that is the rank 2 matrix. What I'm saying is that the pivot columns of not the RREF but of the original matrix, this guy and this guy, the pivot columns will be a good basis for my column space. So what's the column space? Vector, it's got two components, so it's R2, each vector is in R2. So linear combinations will be a subset of R2. What kind of subset will it be? Because I have two vectors that are linearly independent, and that subset is going to be actually all of R2. The pivot columns of A will be a good basis, but since it's spanning all of R2, you don't have to take the pivot columns. You can say it is the identity matrix that is the basis. Just to point out to you, I have two columns that are pivot columns, meaning they have pivots in the RREF. The other columns are ones that correspond to free variables. Now, if you have, that is all full rank matrices, full rank square matrix, full rank tall matrix, full rank wide matrix. Now, if you have rank deficiency, I have a matrix here, A. The first two columns are the same as the A matrices that we looked at, but the third column now is a bit different. What's special about the third column here? Yeah, the third column is just a sum of 1 and 2, so there are only two linearly independent columns. So what's the rank of this matrix A? Rank is 2. If I do RREF, I'll get some matrix like this, 1, 1 and 0. Deficiency now, what's the maximum possible rank this matrix could have? It's a 3 by 3 matrix. It could in principle have a rank of 3, but it has only 2. So the rank deficiency is 1. What's the column space of this matrix? It is a subspace of R3 because each vector, each column is of 3 components, and I have to specify the dimension of the column space, that is 2, which is the same as the rank. So it's going to be a plane of vectors specified by these two highlighted vectors. So a sum space, and the basis would be the corresponding columns in the matrix A. Not in the RREF, because again, this is the x-axis and this is the y-axis. That's not the space that we want. That's not the plane that we want as the column space. It's the plane defined by those two vectors as the columns of the matrix A, pivot columns of A. Now another one here, it is a rank 1 matrix now. There's only one column that is linearly independent. The second column is just twice the first column. And if you do the row reduction, you will get only one row because it's got only rank 1. Everything else will be 0. Rank deficiency is 1. And the column space, again, it is a subspace of R3 because each column of A has 3 components. But dimension is 1 because the rank of A is 1. So it's a line of vectors, and the line is specified by this first column of A. The second column will fall on the same line, and that would be the column space. So the right basis to use would be the pivot column in the matrix A. Now if you take a wide matrix, and if I say that the rank is 1, there's only one row that is linearly independent, so I get some form like this. The second row gets killed by 5 times the first row. The rank deficiency is 1. What is the column space? You take the first column, the pivot column of A, and say that that is the basis of the column space. But how many elements does it have? It's got 2 elements, 2 components. So the column space is a subset of R2. There's a line of vectors in R2 is a subset of R2, dimension 1, and the basis would be the pivot column of A. So